Hello, everyone. Welcome to another Magnimind workshop. I hope you guys are doing well. Today, we are going to work on writing code for logistic regression from scratch. So if you participated in our previous workshops, if you remember, we said linear regression and logistic regression are two very fundamental models that we are going to use in machine learning. So we are going to use linear regression for predicting continuous target variables. We are going to work on problems with target variables which are continuous, like predicting income or predicting the, say, temperature, or predicting height or width of something on an image, right? So continuous variables. So when it comes to classification problems, where we are going to predict discrete variables, which are taking from a limited number of values, right? So they are taking values from a limited number of values, okay? So for example, predicting whether someone is going to pass or fail, predicting whether an email is spam or not, right? Or predicting whether you should give credit to give credit to an applicant or not, right? So these are all decisions that these are all binary decisions, which are classification problems. And for these problems, we might use logistic regression. So linear regression and logistic regression are two very basic fundamental models that we are using. And they can be a very good baseline model that we want to beat later on with some more advanced, sophisticated models. So we can start with logistic or linear regression, and then we can try to improve our model performances. Even though they sound very simple and basic, most of the time they're going to work really well. So I recommend starting from a very simple but working model. Always come up with a model which is working, giving you some meaningful result, okay? And then try to beat that result with more sophisticated models, if possible. Okay, so don't try to target for the most sophisticated, high-performing model in theory. Okay, so try to come up with something that is really working. Okay, so before we start with writing the code, so the documentation at this time, documentation is hello, by the way. So documentation is, we are going to write things from scratch, so we don't need anything. So as of now, so everything we are going to, at the end, if you like, I can share the things that we did in the class. Okay, but otherwise there is nothing to share at this point. So if you guys have a Jupyter Notebook, you can simply open your Jupyter Notebook. If you're not using Jupyter Notebook, you can use Google Colab. So both will work. But before we start writing the code, I just want to go through the mathematical expressions that we are going to use in our coding, right? All right. So again, this is going to be the first time I'm doing this workshop. So this logistic regression workshop. So knowing and practicing something is different than teaching the first time. So please bear with me, all right? So I'm going to start with the very basics, why we are, so the mathematical expressions which we are going to use. Again, without getting into that, it's going to be meaningless starting to write the code, because we are going to code what we have in terms of mathematical expressions. Again, I will try to refrain from getting deep into mathematics, but nevertheless, so we have to deal with it, okay? So first of all, remember from linear regression, again, if you guys participated, so we start with some data set X. Let's use capital X for our data set. So this data set is composed of columns and rows. Each row is corresponding to some person, something, some object. Okay, and then each column will be the attributes. Okay, so let's say I have first attribute, second attribute, and all the way to, let's say, pth attribute. And then I have first, second, all the way to capital N observations. So these can be people, okay, 1 to n. So there are n people, or I can have p number of, or we can have p number of attributes. So I recommend writing the code together with me. again, if you can, if there is any problem, or somehow you could not write the code, or some problem arised, okay, it's okay. So I'm going to share the code later on, all right? But I recommend writing the code with me step by step, all right? Okay, so this is our data set. In addition to data set, we have a target variable. I'm going to use small letter y. Again, x can be, in this case, so x can be, let's say, I have, let's say I'm predicting whether a student is going to pass or fail class, okay? So x can be, let's say, a GPA, current GPA of the student, okay? And then zip code of the student. So that is going to give me an idea about the quality of the high school, let's say, okay? And then, I don't know, maybe age of the student. Okay, so we can come up with our SAT score of the student. So you can come up with different attributes for the student. Again, X is rows are corresponding to students, columns are corresponding to attributes. And Y is whether student is going to pass or fail. So I can use pass with, I can encode pass with 1 and fail with 0. All right. And I have n number of students and p number of attributes. Okay. So let's say this is given, and I want to come up with, because this is so we use a linear model in our linear regression. So I'm going to use the same model here. So what I'm going to do is I'm going to take each of these attributes x1 to xp, and I'm going to multiply them with their corresponding weight. So I'm not going into why we are using weights and that, because we already mentioned that in our linear regression problem. So let's say I'm going to use W1 times X1. W1 is how much weight we are attributing to attribute X1, okay? And then W2 is the weight for X2. So whether GPA is more important than SAT, or GPA is more important than zip code. So that is what W1 and W2 are used for. Okay, so W1, W2 are weights which I'm using to incorporate the effect of these attributes into my decision making. Okay, and then let's say I have p number of coefficients. I'm using the word coefficient and weight interchangeably. Okay, they are the same, xp. Okay, so that is going to be my, in this case, my linear model. Okay, and I'm also going to add my bias term. Let me use this bias term. Okay, b times 1. Okay, this is going to be the bias term, which is going to shift that linear line up and down. Okay, it's going to be offsetting my line. Okay, it's going to be shifting up and down. Okay, so this is going to be, let me use this W transpose X. So what is this W transpose? Suddenly transpose is coming into picture. So if I want to write this in terms of multiplication of inner product of two vectors, okay, so if I say W1, W2, WP, a column vector, and if I say X1, X2, XP, okay, a column, another column vector, then W times X is not going to work. So what I'm going to do is, in this case, W transpose times X. All right. So I can write it this way, or if I'm going to use capital X, remember capital X, I have columns and I have rows. Rows are all these individuals. Columns are the attributes. So if I'm using capital X, then I'm going to use a different format. So what I'm going to do is then X transpose times W. Okay, that is what I'm going to use. Again, when I use X transpose, what I'm doing is, in this case, so that's of course the way I just described is a little bit. It's going to be X times W. Let me call it that way. Okay, because the way I described it requires multiplication of X times W, not transpose. So depending on how we define X and W, so you might need to use transpose or not. Okay, so this is the data. Okay, this is the definition of data. So you can post your questions to QA. Okay. Okay. So let's continue. Now, what I'm going to do is suddenly I'm going to introduce you a function. Okay, so then please, again, we can talk more about this, why we are using that, but I don't want to get into it. It's going to take some time. So suddenly I'm going to introduce a function to you. So that is log loss function. Let me introduce the function first, and then we are going to talk about merits of this function. Okay, so let's say I have some function like this. Okay, so this function is an interesting function. All right, so, and this, let's say this is z. Okay, let's just call it z, and let's call this phi of z. Okay, and this plot of a function. This function, when z is 0, taking the value of 0.5, and as z is getting bigger and bigger, it is approaching to 1. When z is getting smaller and smaller, and then getting into negative side, so getting smaller in the negative side, so this phi of z is approaching to 0. Okay, so as z is getting bigger, phi of 0 is approaching to 1. As z is getting in the negative side, getting smaller and smaller, phi of 0 is approaching to 0. And right in the middle, when z is 0, phi of 0 is 0.5. Okay, if I had such a function, okay, if I had such a function, so I can turn this linear combination of, okay, weighted summation of w's, the x's, weighted summation of x's, weighted summation of attributes. I can turn this w transpose times x, or capital X times w. So these are going to return me some values, right? So for person 1, I'm sorry, person 1, this is w transpose times x1. For person 2, this is w transpose times x2. Again, I'm using x. Let me use a different notation here. Just 1 second, please. x1 and x2. Okay, so this is the value I obtained for person 1, and this is the value I obtained for person 2. So these values, I call them decision function values. Now, remember, I'm trying to come up with a model which is going to help me make classification. Classification requires saying pass or fail. So I want to come up with some value which is going to help me make this classification, 1 or 0, yes or no, okay? So not only that, it would be very nice, in addition to making this decision 1 and 0, it will be very nice if these decisions are also accompanied with or coming with some probabilities. So depending on this decision function value, I'm going to say this student is going to pass. Okay, my decision is pass, which is 1, with probability P1. So the second student is going to pass, okay, with probability P2. If P2 is very small, passing probability will be very small, so my decision will be fail, right? If P1 for the first student is very high, then passing probability very high, and then my decision will be pass. This student will pass, right? So it would be very nice if I had known some probability values which is between 0 and 1. And then if probability is getting closer to 1, my decision will be pass. If probability is getting closer to 0, my decision will be fail for a student. Okay, so this is what I'm trying to predict. So this function phi of z is going to help me come up with that probability values, because it's such a nicely behaving function that it is changing between 0 and 1. And when z is 0, it is 0.5. That means I'm right in the middle of my decision-making process. I cannot say if it is yes or no. I'm in the middle, right? When z is 0. When z is a very big number, then probability is going to get closer to 1. When z is a very small number, then probability will be getting closer to 0. So phi of z is going to give me this opportunity to come up with probability values. So it turns out that this phi of z, I can use a function, which is an exponential function, 1 plus e to the power of negative c. So if I use this function, 1 plus 1 over 1 plus e to the power of negative c. So if I use this function, when z is 0, this is going to be 1 over 1 plus 1, when z is 0. When z is a very big number, this is going to be 1 over 1 plus e to the power of minus a very big number. Then this very big number, it's going to be, e to the power of a very big number is almost 0, right? So that means if z is a very big number, this term is going to be closer to 1, okay? And then, of course, 1 plus e to the power of negative, a negative number will be a positive number. So let's say a very big number, a very big negative number is going to approach to 0, because e to the power of a very big number will be a huge number. 1 over a huge number will be 0. So this phi z equals 1 over 1 plus e to the power of negative z. It's going to be a well-behaving function which I can use to turn my decision function values into a range between 0 and 1, which is going to almost look like probabilities. Okay, so that will help me make decisions based on some probabilities. So I started with my data set. My data set has columns. Each column is an attribute. Each row is an observation. And I have this target value, but this time target value is taking discrete values, 0, 1, yes, no. And then similar to linear regression, I want to use these weight values. Weights are going to determine how effective these attributes are in terms of making my decision about whether this student is going to pass or fail within this context, right? So then I am using this function, okay, to turn my decision function value, to squeeze in my decision function value in between 0 and 1, so that I'm mapping my decision function value to a value between 0 and 1, which is going to look like probability. Here, z is going to be W transpose times X. Again, W is my coefficients or weights. X will be my data attributes. Okay, so this is just the beginning. Okay, so we know what phi of z is, what z corresponds to, what W corresponds to, what capital X is, what Y is. Okay, now, hold on, I just pay attention to. Yeah, the recording will be available. How close it has to be before this site? So again, that's another question. So this 1 over 1 plus e to the power of negative c, where z is our decision function value, right? So let's say we want to use a threshold of 0.5. Okay, so if phi of z is greater than or equal to 0.5, my decision is 1. If phi of z is less than 0.5, my decision is 0. So in general, by default, most machine learning algorithms, when you use logistic regression from scikit-learn, the threshold that you are making, you are using to make this decision, 0, 1 decision, is 0.5. Okay. Well, it's up to you. You can change this decision. So you can say if phi of z is greater than 0.2, I'm going to make a decision of 1. If phi of z is less than 0.2, I'm going to make a decision of 0. So again, this is up to you, how you set this threshold. Oh, we can talk more about this. What is the impact of this threshold? It's a different story. So evaluating classification algorithms, how you set your threshold, that depends on how your ROC curve is going to look like. So let's not get into it, but you can change this threshold to make your decisions differ. Okay. So you can be more strict about your decision-making process by reducing or increasing your threshold. It's up to you. But here we are going to use 0.5 by default. Okay. All right. So now we get into probability. All right, probability. Let's use this notation. Okay, please bear with me for maybe 15 minutes. Then this is going to be over, and then we are going to start coding. All right, so I said we get into probability. We have X and we have W. Okay, W is the coefficients, X is the data for each individual, in this case, set of attributes. So given X and W, I'm using mathematical notation, okay, given X and W, I'm going to predict what is the probability that my target value is 1. What is the probability that my target value is 1 given X and W? Somebody gave me X. Somehow I got a set of coefficients for this X. Okay, I multiply each X with its corresponding W. Okay, given and then sum that up. That is my decision function value. Given this decision function value, what is the probability that my decision is going to be 1? Okay, that is what I'm interested in, let's say. Okay, so this is actually nothing but that phi of Z, where Z is W transpose X. Okay. So again, remember what is phi of Z? 1 over 1 plus e to the power of negative C. Okay. All right. So again, if phi of Z is closer to 1, then my probability, the probability that Y is 1 is going to be very high. If phi of Z is 0, the probability that Y is 1 is going to be very low. Okay. So I'm using this notation, the probability. Well, then what is the probability that Y is going to be 0? Given the same X and W values, then it's going to be 1 minus phi of Z. If phi of Z is probability that my decision is going to be 1, then 1 minus phi of Z is probability that my decision is going to be 0. Okay. All right. So I'm using probability. So I came from X and W's, and then suddenly I went into the realm of probabilities. Okay. All right. Next. So now what I'm going to do is, somebody gave me n number of observations. This is going to be my training data set. I will use this training data set, okay, to find W's. This is my goal. I want to find the W's, which is going to help me make the best decisions, the decisions that are the closest to the reality, the true values of the target value. All right. So my goal at the end of all this process is finding the W's. Okay, that's my goal. So somebody gave me a set of data points and told me that here are a set of data points, and these are the corresponding target values. So there are some students in the past who took this class, they failed or they passed. So I know they failed or they've passed. Okay. And then I know their attributes, and somebody gave me this as a training data set. This is my training data set. So this happened in the past. So I'm going to use this to train a model and find these W's so that I will be using this for the future data points. Okay. Now I'm going to put all my data points and number of students that I have their data from past. Let's say I'm going to use student 1, student 2, student n. So each of these students, some of them passed, some of them failed. Let's say this is 1, student 3, 0, student n minus 1, let's say 0, 1. 0 means failed, 1 means passed. So S1, S2, these are students. Actually, 1 and 0s, these guys are the target variables, right? Okay. All right. Now I know whether this student passed or failed. So what I'm going to do is, this student passed, right? So then if I had a model, okay, if I had a model, I would be interested in whether my decision is going to be 1 given this student, okay? So X1 and W. W will be the same for all students, but each student will have his or her own X, right? X1 is the first student's attributes. Okay, and then I'm also interested in the second student, whether she is 1 or not, given her data and the W. W will be the same for everyone. And I will continue this way. Y is 0 given, okay, X n minus 1, W, so on and so forth. Okay, so I'm assigning a probability for each student, and that probability is a function of W. So my goal is finding that W. So these probabilities should be coming up with some values which are going to be close to 1 if the student passed and close to 0 if the student fails. So how close these P values are going to come to the true values depends on what W I'm going to pick. And this may not be an easy decision because remember, W's are going to be same across all students. Okay, so that's why I have to compromise. I have to find a W which is sometimes going to make me wrong decisions, which is okay. Okay, which is okay. All right. Now, given my data, given my data, and assuming some W, which I want to find that W, but let's start with some W. That's what we're going to do in coding. We're going to start with some W. I want to maximize the probability of these, the multiplication of these probabilities. So this is the probability that the first student passed. This is the probability that the second student passed because she passed. This is the probability that this n-1 student failed. So I want to maximize the multiplication of these probabilities. So I want to come up with a model with the same W across all students. That is the key, the same W across all students. That's why I'm multiplying their probabilities. Okay, so that W is going to be such a W that when I multiply individual probabilities of students, that multiplication is going to be maximized. Okay, so that is actually what I want to maximize. All right. Okay, so they're getting close to the coding part. Okay. Now I'm going to use a mathematical notation. Okay. So what I'm going to use is this pi. Okay. Okay. This is from the first student to the nth student. I am multiplying, okay, their probabilities. Yi given xi w. Exactly what I wrote here. Okay. This is the first probability times the second probability times the third probability. That's what I'm doing here. Okay. So most of the time for optimization problems, we don't like multiplications. We want to turn them into summations because summations are going to make our job a lot easier. Okay. So what I'm going to do is, before getting into summation, by the way, I'm going to write this multiplication in a simpler format. Okay. So what I'm going to do is the following. Okay. Following. You know what? So I know that this probability is nothing but phi of z. Remember? Probability is phi of z. So what I'm going to do is I'm going to take phi of z and then to the power of yi. Okay. And then I'm going to multiply this by 1 minus phi of c. I will explain why I'm doing this in a moment. 1 minus yi. So why did I do this? What is this? All right. Remember the first student passed, second student passed, but third student failed. Okay. So that means the first student's target value is 1. The second student's target value is 1. The third student's target value is 0. Okay. So this is the probability for the individual students. So this probability is nothing but phi of z. So then what I can do is, if the student passed, by the way, this is 1. If the student passed, it is phi of z. If the student passed, it is phi of z. If the student failed, it is 1 minus phi of z. Okay. Then what I can do is take the probability and make it to the power of, so what I can do is I can take phi of z to the power of y and 1 minus phi of z to the power of 1 minus y. If I do this, let's say a student is passing and y is 1. If y is 1, this term is going to disappear. I will only have phi of z. If y is 0, then this term is going to disappear. I will only have 1 minus phi of z. So what I'm doing is I'm turning this p into either phi of z or 1 minus phi of z, depending on if the student passed or failed. If the student passed, I will have phi of z. If the student failed, I will have 1 minus phi of z. Remember, this probability is phi of z if student passed, 1 minus phi of z if student failed. All right. So that's why I turned the probability into this format here. That's the only reason. So I just saw the question. Sorry. I'm a bit confused with y and w. Again, y is target variable, whether passed or failed. W is coefficient, okay, or weight. So I'm multiplying w by x. X is data attribute. Okay. What is W here? W is coefficient and weight. Y is target. W is coefficient. Why is W same for everyone? I cannot come up with a W different for everyone. So that is why logistic regression and linear regression are simple and basic. Okay. So I want to come up with this with a set of coefficients which is going to be the same for everybody. So that is the difficulty. So I will set a W which is going to be the same for everybody. But it will help me make decisions for each individual differently. All right. So that is the difficulty of W. Just 1 second, please. I just solve. Sorry about that. There are people working in the backyard and they were about to break something. So I had to tell them, sorry, sorry. Okay, so W is the weight and X is data. W times X is going to be, so W will be the same for everyone. That is the difficulty, okay? But it's also the simplicity. Now, I just want to check if this part is okay. This part is okay with everyone. If you have any questions about that one, let me answer. If it is okay, I will continue. Without understanding this, writing the code is very simple, but then we are going to ask, why are we doing this? Why did we use this expression? So first we need to understand why we are using that expression. All right. So I think this part is easy to understand. So again, the probability is phi of z. Remember how we came up with phi of z. And if p is 1, we're going to use phi of z. If p is 0, we're going to use 1 minus phi of z. So that is depending on yi. Okay. If y is 1, we're going to use this one. If y is 0, we're going to use this one. All right. Now let's continue, guys. So what I'm going to do is now I am going to take the logarithm of this pi. So remember from our high school and maybe college days, logarithm of x times y is logarithm of x plus logarithm of y, right? Logarithm of x times y is logarithm. Then what I can do is logarithm of multiplication of the pi is multiplication of a series of numbers, let's say z. Let me use a different logarithm k, I is from 1 to n. This is nothing but logarithm of ki, and I is from 1 to n. Summation of logarithm of ki's. Okay, I'm repeating. This is nothing but k1 times k2 times km. Okay, if I take the logarithm of this, this is going to be turning into log k1 plus log k2 plus log km, which is nothing but summation of log ki. So I turned a product into summation by taking the logarithm of the product. When I take logarithm of the product, I'm turning into a summation of logarithm of individual elements in that product. Okay, I'm going to use this. All right. So I will take logarithm of pi. We know what this is now. Times I is going from 1 to capital N. Capital N is number of people, number of students in this case. So this is going to turn into a summation of logarithm of yi times logarithm of phi of z plus 1 minus yi times logarithm of 1 minus phi z. Okay. So please keep in mind, logarithm of a to the power of b is b times logarithm of a. So this only works for binary classification. Yes, so we can always use multi-classification problems, solve multiple classification problems using binary classification. So that's why we are going to focus on binary classification. Can you have different values of W for different attributes? If you are changing your data set, of course, your Ws are going to change, but for each attribute, W will be different. So W0 will be for the 0 attribute, W1 will be for the first attribute, W2 will be for the second attribute, and WP will be for the pth attribute. So these are the attributes for each person, but these Ws are going to be, so each W, there is going to be a different W for each attribute. Attributes will be different across users or individuals or objects, but the set of Ws will be the same for everybody. The difference between coefficient and features of X. So again, coefficients are capital X. Okay, I have person 1, person 2, let's say person N. This person has GPA, okay, gender, zip code, high school, family income. Okay, these are all attributes. Okay, so these GPA, gender, zip code, high school, family income will be different from one person to another. Okay, will be different from one person to another. All right. Now, for each of these attributes, I'm gonna come up with a coefficient. Okay, so for GPA, I'm gonna have W1. For gender, W2. For zip code, W3. For high school, W4. For family income, W5. So these Ws are going to be the same for everybody. Okay, but each W value will be different for each attribute, right? So what is K? K is just, I just use an example. What if you multiply K1, K2, K3, all the way to Kn? So there are N values. Each one I'm using a variable K. K1 is the first number, K2 is the second number. I multiply them. If I take logarithm of this multiplication, I'm actually summing up logarithm of individual variables. Okay. W always same amount. Okay. So W1 is for GPA, W2 is for gender, W3 is for zip code. So each W corresponds to a different attribute. So once you find this set of Ws, it's one vector, a single vector. That W will be the same for everybody. So if a new guy comes, okay, if a new guy comes, and then I want to know whether this guy is going to pass or fail. So I'm going to ask this new person, what is your GPA? What is your gender? What is your zip code? What is your high school? What is your family income? Okay, I got all this information from this guy. And then I'm going to multiply GPA by W1, gender with W2, zip code with W3, high school with W4, and family income with W5. So this is guy 1, okay, the first one. If I get another guy, another person just showed up, I'm going to ask this person's GPA, gender, zip code, high school, and family income. Of course, this person's values will be different, but I will still use the same Ws for this second person too. So Ws will be the same across all individual users. All right. Yeah, zip code and high school are categorical variables. They have to be one hot encoded. Yeah, that's for about pre-processing. Okay, so let me continue with this one. I know that for some of us this is very basic and easy. For some of us, it's going to be very might look very different and difficult. But again, without this, it's going to be meaningless to write the code. Okay, so remember what I did. I started with a data set and target variable. And then I said, can I use some function where Z is going to be some coefficient times X, And this function is going to give me the probability values between 0 and 1. My goal is turning this linear equation through this transformation function into a probability value between 0 and 1. And if someone gives me a training data set, my goal is maximizing the probabilities across all users given X and some W. Now, my goal is finding this W, which is going to maximize the probabilities of making the correct decisions across all users. Okay, that is my goal. That is why I came up with this equation here. This equation here. This equation. This equation is I'm multiplying probabilities for each individual, n number of probabilities. I'm multiplying them. I'm going to make a collective decision for everybody. Okay, that's why W's will be the same for everybody. Okay, almost there, almost there. Now, because I was maximizing the probabilities, now I'm going to put a negative sign in front of it, and then I will minimize it. Okay, I'm going to put a negative sign and minimize it. I'm going to use L for that. And then here is what I'm minimizing. Okay, this is what I'm minimizing. All right, so to minimize this function, I'm going to take the derivative of this whole thing with respect to W. Remember, Z is W transpose X. I'm trying to find this W. That is my goal. That's why I started doing all this job. Okay, I want to find the W, which is going to minimize this expression. So I'm going to take the derivative of L with respect to W. So derivative of L with respect to W is nothing but derivative of L with respect to phi of Z. I'm using chain rule here. Derivative of phi of Z with respect to Z and derivative of Z with respect to W. Okay, again, those who have not seen this before, I understand, okay, that at this point, I mean, it's gonna take a lot for me to explain what this is doing, okay? So this is chain rule. I'm taking derivative of L with respect to W. So I first take the derivative of L with respect to phi of Z, phi of Z with respect to Z, Z with respect to W. So that means I'm taking derivative of L with respect to W. Why am I taking derivative of L with respect to W? Remember from our linear regression session, my goal is I want to solve this problem iteratively. At each iteration, I want to update W's from some starting point. I want to update my W's with small steps. I want to make a decision on which direction I should take this small step. So remember from our discussions on linear regression, if this is my loss function, which is the difference between true values and my predictions, which is error. Okay, so if I start from some point here, I want to reach to this minimum point step by step. To make this step by step, I'm going to take small steps towards this minimum. Okay, that is my goal. So if I take big steps, there is a danger that I'm going to step over the minimum and then starting going up. Okay, all right. So I want to step by step, start from somewhere, step by step approach to this minimum point. So to do that, I'm going to be using derivatives. Derivative is going to tell me whether I should go down or up. If I start from here, I need to go this direction, not this direction. If I start from here, I need to go on the left direction. If I start from here, I need to go in the right direction. So I need to make a decision on whether I should go left or right. That decision going towards left or right is going to be based on the sign of this derivative. just trust me at this point, all right, if you are not familiar with this. Okay, if we take the derivative of this, again, let me write the rest of it for you, and then I will share this as a good, nice, I'm gonna type this and then share it with you. So if we take derivative of W, derivative of L with respect to W, the resulting equation is going to be the following. The intermediate steps, I'm gonna type them for you. Let me not get to that one now. This derivative is going to be the following: yi minus phi of z times x. Okay, let me stop here. All right, so this is the error. Remember, this is the true target variable. This is decision probability. The difference between the true target variable and decision probability is the error, and this is my attribute or data. All right. So what I'm going to do from this point on is I skip some of the steps because I realized that some of us, may need some a little bit more background. So I think I should not get into more details at this point. I'm going to type this and then share with you. If you like, you can go through the steps yourself. Okay, now let's come to the coding. Okay, what we are going to do. If you go and check any the machine learning algorithms, specific, let me talk about scikit-learn, you're going to see three things: fit, predict, score. Okay, fit, predict, and score. Fit, what fit is going to do is it's going to give you these W's. Predict, what it's going to do is taking these W's, multiplying it by attributes for a new data variable, and then make a decision. Pass or fail. Score is going to, and this decision is going to be y hat, your prediction. The score is going to tell you how you did in terms of how close you got to the true values. So it's going to compare your predictions with the true values. That is the score. So any machine learning algorithm with scikit-learn is going to, estimator is going to come up with these three functions: fit, predict, and score. Okay, so we are going to start with fit. For fit, we need the following equations. We just what is that? Yeah, gradient descent, Heraldo. So we just came up with this one, which is yi minus phi of z times x. To fit, what I'm going to do is I'm going to start with some w, and then I am going to update this w, okay, with some step size. That step size eta is this. If step size is big, there's a danger that I'm going to step over the optimum point. If step size is small, it's going to take forever for me to get to the optimum point. So I need to be careful about how big the steps I'm going to be taking. Okay, some eta times this derivative. So this derivative is going to tell us the direction in which we should go. Okay, and also how much we are going to increase W's, and that how much increase is going to be weighted by the step size eta. Okay, so fit is going to step by step update the W's. How many iterations? In this case, I'm going to say 5,000 iterations. In 5,000 steps, slowly, we're going to update W's until our W's are going to be closer to some value that is going to minimize the difference between our predictions and true values. So somehow we are assuming that we are getting closer to this optimum point. So this whole thing is called gradient descent. Okay, so that's what we're going to do with fit. When it comes to predict, it is very easy. With predict, what we're going to do is we are going to take this W that we found from fit and then multiply it by X, and then check if it is greater than 0.5 or not. So 0.5 is our threshold. If it is greater than 0.5, we're gonna say 1. Okay. Otherwise, we're gonna say 0. All right. That is predict. With score, we're gonna do 4 things. First, we are going to find true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. What is true positive? True and false are attributed to our predictions. Let's say a student passed and we predicted as passed, then we have a true positive. Let's say a student passed and as we predicted failed, we have a false negative. A student failed and we predicted pass, we have a false positive. A student failed, we predicted fail, we have a true negative. Assuming that pass is positive, fail is negative. Okay, so with score, we're gonna find first this one, we're gonna call this accuracy. And then we are going to find true positive divided by true positive plus false negative. We're going to call this precision. And then true positive divided by true positive plus, what is that? False positive. We're going to call this recall. And then 1 over precision plus 1 over recall. We're going to call this F1 score. I'm not going to get into these now. Okay, these are another lecture. And we're going to find each of these for score. So that is what we're going to do. Okay, 3 things. If you're ready now, let us start working on the, so there are sometimes we also see fit transform. How is it different than fit? So fit transform, we are using for transformers. With scikit-learn, we have estimators and transformers. Estimators like logistic regression, linear regression, we are making predictions. With transformers, we are transforming data set, like scaling the data set. Okay, so with transformers, what we can do is we can fit and then transform. Okay, that's when we are using fit transform. Repeat, fit, predict. Yeah, fit, predict, and score. Fit is for finding the optimum W. Predict is predicting, making a decision, right? Predicting whether someone is going to pass or fail. And score is going to tell us how well our predictions worked. So logic is not a closed form solution. The W's could be different based on number of iterations. Yes, yes. So closed form solutions are expensive when it comes to machine learning algorithms. So that's why we are using this stochastic gradient or gradient descent algorithms, iteratively trying to find W's. And depending on number of iterations and eta value, you are completely right. W's are going to be different. Yeah. Okay. Let me stop sharing the screen at this point. Stop sharing this one. And yeah. Okay. Now, there are some questions about whether we have any beginner program for beginners. Yes, we have a program for beginners, full stack program for beginners. So we are teaching Python and mathematics and statistics, SQL and machine learning, and NLP. Okay, so it's going to be a 17-week long. I think the next batch is going to start in September, on September 24th. Okay, so the next batch is going to start Magnimind full stack program on September 24th. So if you are interested in learning all this, I mean, as a beginner, maybe you can consider that program. Okay, so it's going to be more all face-to-face, like not face-to-face, synchronous online classes. So maybe we will get to this, but where does the intercept term come from? So the intercept term, here we mentioned that it's going to be offsetting the linear line. Okay, it's going to be shifting it up or down. Okay, let me put this aside. and start writing the code. Now, let's see. Okay, it's going to be a little bit challenging because I couldn't finish the whole mathematics that I was planning to, but it's okay. So let's start with importing Numpy. Import Numpy as NP. So we are going to be using Numpy vectors and matrices. So that's why we are going to be using Numpy. Okay. So let me run this. By the way, you are ready, right? You are ready to start with this. I can wait if you guys are going to open your Google Colab. Okay, so the program takes 17 weeks. You are going to get the recording of this class. I'm not aware of any scholarships per week. It's going to be 5 hours of class time, and also you're going to have TA sessions. Okay, live TA sessions. And another thing is, please check on the review pages, and then don't forget to post reviews about Magnimind or these workshops. It's just encouraging us to give more workshops. And then let us know whether we are doing well or not so that we can adjust our teaching. All right, so I'm waiting for you guys. If you are ready, I can start. If you need any help with Google Colab, I can tell you how you can start Google Colab. I think we are ready. Okay. So we are going to import Numpy. Next thing is I'm going to create some artificial data set. Okay. So from scikit-learn data sets, I'm going to import make classification. Okay. And then I am going to, this is just for creating some artificial data set. All right. So don't worry about this part. I'm creating an artificial data set with 4 columns and 2 classes. Okay, 4 columns and 2 classes. Okay, so make number of features is 4. Okay, and then number of classes is 2. Okay, again, don't worry about this. It's just an artificial data set. Let's see. If you check the shape of X, I created a data set with 100 data points. Each data point has 4 columns, 4 features. Okay. And then if you check the shape of Y, this is the target variable. If you check how Y looks like, sorry. So it is just 0, 1. Okay. This is a classification problem, 0 and 1. So that is my training data set. Now, if you wish, we can divide this data set into test and train data set. That will come later. Let's start writing our code. Okay, writing our code. I'm going to be creating a class for our code. Okay, and please let me know if you have any questions. Okay, please let me know if you have any questions at any point. Okay, so let's create our class first. Class, I'm going to call my class as Logistic Regression Gradient Descent. You can call it anything you like. Okay, you can call it anything you like. So in this class, I'm going to have 3 main functions. So remember, with classes, we are putting together functions, right? So I'm going to have 3 functions. One is the function will be fit. Okay. Another one is going to be, let me do this. Another one is going to be predict. Okay, predict. Okay, and another one is going to be score. Okay, so there are going to be 3 functions. You can add more functions if you want to create a more modular code, right? Okay. So, of course, for any class, the first function is going to be, what is that? An init function. So let's first start with our init function, define init function. Okay, this init function, whenever we call log reg gd, so let's say later on, what we are going to do is we are going to say logistic regression equals log reg GD. So that's what we're gonna do, okay, later on. So the moment we do this, we are taking one instance from this class. This is a model, a logistic regression model that we initiated. So when we first initiate this model, this function is going to run, okay, this init function. When we first initiate, it's going to run. Every time we initiate a new logistic regression model, this function, init function, will run. So this function has its own parameters. Of course, self. Okay, self is at first it's difficult to understand or explain, but self is the moment we create this lreg, so it is going to come up with its own self attribute. So this is what self is referring to. Okay, self is referring to this object itself. Okay, so what kind of attributes? Eta is, remember eta, it is the stepping size. Okay, let's call it 0.01. Again, this is a hyperparameter. You can change it. You can give it different value, 0.05. Number of iterations. Remember, I said 5,000. Well, you can give another number if you like. And then I'm going to use a random state here. What is random state? Random numbers generated by computers are actually coming with random state. Random numbers generated by computers are coming with a preset random sequence of numbers. So I'm using a specific random sequence here. So if all of us set it to 1, they are going to use the same random sequence of numbers. Okay. Now self.eta is eta, which is this. Okay. If when I call this function, if I don't specifically assign any eta value, this is by default, this is the eta value that I'll be using. Okay. Self dot number of iterations is this. And then self dot random state is this. Okay, I'm done with the init function. Perfect. Let's now work on the fit function. This is going to be the most challenging one. Okay, the fit function. Yeah, instead of loading scikit-learn, can we achieve the same with only Numpy and pandas? Yes, you can do that. But it's going to be a lot easier for us to do it with scikit-learn at this point. Okay, so let's talk about the fit function. For fit, of course, I will first use self. Okay, every time you call a function in a class, the first parameter is self always. And then, of course, I need x and y. Remember, x is the attribute set, y is the target variable. Okay. All right, now let's remember all these mathematics that we talked earlier. Okay, we have to remember all that. First of all, I need to begin with, I need to assign some initial values to w's. I cannot assign all zeros as initial values to w. Remember, what is w? W is the coefficients. I will slowly update coefficients until I reach to a point that, you know what, w's are close enough to give me good predictions. Okay, so, but I need to start from somewhere. That somewhere it's not 0. Do not start from 0. We're just going to assign some random numbers to w's. For that, I'm going to generate a random number generator. Okay, so let's see. My random number generator is this. I will use from Numpy's random. What is that library, and then I will set its random state, okay, to the random state. This part is not very critical. I'm just using this so that all of us are going to use the same random numbers. That's why I'm using this. So my random number generator is set to a random state that I set here, which is 1. Okay, now I will use this random generator. Okay, this one. Okay, I will create a normally distributed random numbers with mean value 0, standard deviation 0.01, and in the size of my data set, x dot shape. Okay, let me talk about what this x dot shape is. Remember, this is x dot shape, 100 data points with 4 attributes. If I say x dot shape 1, okay, it's gonna give me 4. So what I'm doing is, remember, I'm gonna assign a W for each attribute. I have 4 attributes. I need 4 Ws and 1 intercept. 5 Ws, 4 of them for the attributes, 1 of them is the intercept, okay, or bias term. So I have 4 Ws. I'm gonna assign a normally distributed random variable. I'm gonna assign this, I'm gonna create random numbers from a normally distributed random variable. 4 random numbers. This is what 4 random numbers, which are very small with mean 0 and standard deviation 0.01. So let me show you what happens here. Okay, as you see, I just generated 4 random numbers, okay, with 0 mean, standard deviation 0.1, and the size is 4. So if I make this 400, let's say 4,000, okay, let's call this some C, okay. If I check the mean of C and standard deviation of C, as you see, the mean is almost 0 and standard deviation is 0.01. So if I change the standard deviation to, I don't know, 0.6, then I will have a standard deviation of 0.6. So I'm generating 4,000 random, normally distributed random numbers with 0 mean and standard deviation 0.6. Here, I'm generating 4 random numbers with 0 mean and standard deviation of 0.01. That is going to be my initial W's, okay? This is gonna be my initial W's. So let me say self dot W's. I'm gonna use underscore for W's. That means I'm generating these W's as part of this code. Okay? So you can give any name here. Let me not use W underscore. It's going to make you maybe, let's use weight. Okay. All right. This is my weight, which is initiated as of now. So I just assigned an initial value to 4 weight components. Each component is corresponding to 1 attribute. Next, after weight, I'm going to assign an initial value to my bias term or intercept. So let's assign this to 0. Okay, 0. Bias term, you can assign an initial value of 0. For weight, no. Okay, now I'm going to update my W's iteratively. So how many times? 5,000 times, because that is number of iterations. So for I in range of self number of iterations, so 5,000 times I'm going to iterate my W's, right? First of all, I'm going to find the Z, right? Remember what Z was? Z equals W transpose times X. So I'm going to find that. Z equals dot product of NP dot of X, which is X times W and self dot weight, okay, plus self dot bias. So what is this, guys? This is Z equals W transpose times X plus bias term. Remember, we learned about this. I'm just using that here. NP dot is dot product of a matrix by a vector. Once I find Z, next, what I'm gonna do is I'm going to find phi of Z. Remember what phi of Z? 1 over 1 plus e to the power of negative Z. That's what I'm gonna do. So let's use this phi of z is 1 over, okay, sorry, 1 over, all right, 1 plus, I'm taking the exponential of z, okay, negative z. Okay. Remember this one? We already talked about this. Phi of z equals 1 over 1 plus exponential negative z. Okay, I use this expression. Okay, this is going to be the probability. Remember the probability between 0 and 1. Oh, there are a lot of. Is there a reason to use random not fitting each parameter pairwise to the target? So there is a reason why we are using random, because we have to start from somewhere. For the W's, we have to start from somewhere. I don't know where to start, because I want to find W's. If I knew where to start, I wouldn't even bother finding W's, because I know W's, right? So because I don't know what W's are, and I have to start from somewhere to iteratively update W's so that I can get closer to a point where W's are well enough that my predictions are closer to the true values, I have to start from somewhere. If I assign zeros to W's, this Z will always be equal to 0. Look, Z equals W times X. If W's are all 0, 0 times X will be 0. So Z will always remain as 0. I will not be able to update the W's, because Z will always be 0. So that's why I have to start from somewhere. I assign some random numbers to W's, which are different than 0, most likely. So then I can start from somewhere and then begin updating W's. Okay. All right. Now it is time for us to update W's. So for that, first of all, I need to find the error term. Remember, what is error? Error is difference between y, which is the true target value, and phi of z. Phi of z is the probability, remember. Okay, that is the error term. All right, I found the error. Next, I'm going to use this error to update my W's. So this is my weight, my W. I'm going to take my W and update it by eta times, again, referring to mathematical part that we learned about, eta times the derivative of L with respect to W, which gave us the following, times X transpose dot product. I'm going to tell you what this means in a moment, errors, okay? And then I'm going to normalize this by the number of data points. Okay, now let's see what I'm trying to do. Look, X dot shape. I have 100 data points. I am adding up all the errors for individual data points. I'm adding them up, and then I'm dividing by number of data points. So this is my average error. This is my average error. Okay, that's why I'm dividing by 100 here. Okay, what is this X transpose business here? Let's go back here. So if I were to multiply X dot Y, okay, if I do this, X dot Y, this is nothing but X Y, okay, X times Y, basically. It's going to give me an error. It says X is in the shape of 104 and Y is in the shape of 100. It's not aligned, because when you multiply two matrices, in this case, a matrix with a vector, so this guy has to be, its number of columns has to be equal to the number of rows of the second one, right? So that's why I'm taking the transpose of this. Now it's going to multiply. All right, so that's why I took the transpose of X in here. Okay, so I updated weights. Now it is time for me to update the bias term as well. Okay. Plus eta times X transpose. Actually, in this case, X, so there is no X for bias term. This is 1. So it's simply errors, the mean of errors. Errors dot mean. Okay. Eta times errors. Because for the bias term, X is 1 for the bias term. And when you take the derivative of W times 1 with respect to W, there is no X remained. So that's why you can say this summation of mean. Okay, summation of errors divided by. So I can do this here. Errors at mean is the same with summation of errors divided by X dot shape 0. These are the two. These are the same things. Okay, I updated the bias term as well. Let's see. Errors is not defined. Oh, error. Let's use errors here. Okay. I just defined it here. Okay. All right. Thank you. Thank you for the. We are almost there, guys. So we updated W. We updated bias term. That's it. So we are going to update weight and bias for 5,000 times. Now let's return self. When we return self, anything coming with self will be returned. Bias, weight, okay, Y, X, all this, and then what is random state, number of iterations, eta, they are all returned here. Okay. Errors. Okay. Now let's work on the prediction. I think we are done with this part. So let's now work on the prediction. So how do we do the prediction? It's actually very simple. So for prediction, we need self and X. That's it. Because I'm going to take X and multiply each X by W's. And then I'm going to see summation of X times W's is greater than 0.5 or not. Okay, let's do it. I'm going to take X. So that actually, I'm going to do exactly this one. Okay, I'm going to take X multiplied by the weights and then add the bias term. Exactly this one. Okay. All right. So I found Z. Now what I'm going to do is I am going to decide whether Z is greater than or 0. So what I'm going to do is return NP where Z greater than 0.5. Whenever Z is greater than, let's also use equal to 0.5. So it's going to be the same as we discussed. Whenever it is greater than 0.5, return 1, otherwise return 0. That's it. That is prediction. So we're done with prediction. It's very simple. All right. Now let's work on score. So for score, again, we need self. Okay. In addition to that, I need Y, which is my true label values, and I need my predictions, Y hats. So I'm gonna, if you like, you can find Y hats outside, and then what is that? So here for prediction, what you can do is, let me see. Self Y hat. Okay, so again, we can first find Y hat and then call the score. Okay, I think this is fine. Let's continue. All right, now remember, I'm going to find accuracy, precision, recall, and F1 score, all that. Okay, so let's assign all 0 values to true positive, true negative, false positive, false negative, to 0. Okay, all these guys are 0 at the beginning. Now, again, you can do this in a much better way without using for loop. I'm going to make it simpler. Okay, for I in range of length of Y. Okay, I'm going to go through each and every target variable. Okay, for the first student, for the second student, for the third student. Okay, if, again, you can do this in a much better way. If yi is 1, I'm sorry. if yi is 1 and y hat is 1, okay, is 1, all right, then true positive is true positive plus 1, okay. So that means I got a true positive. Okay, I'm making this simple so that all of us follow what true positive, what for the true negative means, all right? So I'm going to write else if. Okay. I'm just going to copy this to make things easier. So if yi is 1 and y hat is 0, that means the true value is 1, but our prediction is 0, then we have a false negative, right? So then false negative is increasing by 1. Okay, let me copy this. Another, sorry. Okay, again, this time if yi is 0 and y hat is 0, then true negative is increasing. Okay, one more. If yi is 0, y hat is 1, that means it was negative, but we predicted positive. So our prediction is false. False positive is increased by 1. Again, you can do this in a much elegant way. Say prediction to self. Yeah, you can do that. You can do that. So let me say self. And then let's return this one. What is y hat versus y hat? Y hat is the, oh, did I use different? Oh yeah, thank you. Let's change this to y hat. Okay, yeah, they have to be the same. I use different notations. Thank you. All right, so we now have true positive, true negative, false positive. What is left is just find accuracy. Accuracy is true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. Okay, this is accuracy. Now recall, let's call it precision. True positive divided by true positive plus false positive. That is precision. Recall true positive divided by true positive plus false negative. Okay, and F1 score, F1 is 2 times precision times recall. It is basically 1 over or 2 over 1 plus 1 over precision plus 1 over recall. Okay, times recall. Okay, divided by precision plus recall. Okay, precision. I hope I did all correctly. Please correct me if I did wrong, okay? All right, now let's return these guys. Return accuracy, okay, precision, okay, recall, okay, and then F1 score. I hope we did everything correctly. If I have not done anything wrong with what is that? That's I'm typing. Let's see. Now, okay. Now let's instantiate our model. Let's see. Okay, we got the model array. Now, what I'm gonna do is I'm going to divide. Let's not divide it into test and training data set. Let's simply use our training data set. So our model is lreg dot fit x and y. Okay, so let's hope that it's going to work. Oh, it worked. Okay, now let's hope that it's going to give us good values. So y prediction is, let's use y hats. So that's what we used, y hats. Now lreg dot predict. So I'm going to use just x in here. So hope that is going to, oh, it worked. Okay. Now let's see if the score is going to work. Okay. So score lreg. Okay. So for score, I need y and y hat. Okay, it gave us the scores. So accuracy, what was that? Precision, recall, and F1 score. Now, what I'm curious is, let's check the weights. These are the weights, and you see there are 4 weights because we had 4 attributes and bias. Okay, now let's do this. Okay, let's import scikit-learn and then compare our results from scikit-learn linear model logistic regression. Okay, so let's call this LG or LR. Logistic regression. Okay, we'll do the same things. Okay, lr.fit x and y. Hopefully, we're gonna get the same lr. Coefficients. Okay, I'm more interested in coefficients. Hopefully, we get the same coefficients. That means everything will remain the same. Intercept. Coefficients are coming differently. Not so different, but you see they are not so different, right? So 0.58, 0.55, negative 7.72, negative 0.68, 0.93, 0.88, 0.3. So coefficients are pretty close, right? So let me see. Yeah. So if I increase number of iterations, let's see, where is number of iterations here? Maybe it's going to be better. I don't know. Let's see. I mean, so it's not just number of iterations. We need to change eta as well. But I think the coefficients are pretty close enough to what scikit-learn is giving to us. So I know the mathematics was a little bit, for some of us might be too much. But without mathematics, it's going to be really meaningless to go through this code. I still feel like we didn't do a good job in terms of explaining mathematics behind this part. As I promised, I'm going to type what I tried to explain and then share it with you. So when I share that, I'm going to share this file with you too, in case you could not type it. All right. But this is all about logistic regression in terms of writing a function to fit and predict and get the score on your model. Okay, so thank you so much for listening. I'm going to stop here. Please don't forget to post reviews. If you have any suggestions, please let us hear from you. And if you're interested in the full stack bootcamp, again, the next batch is starting in September, on September 24th. So thank you, and I will see you maybe next time. I don't know. Okay, take care, guys. Bye.